All right, here we go. So there's this thing called the second derivative test for Local Extrema. Don't get this confused with this one. All right, guys, focus. Don't get this confused with this one. I know I call this a second derivative test as well, but notice the big difference is this is a second derivative test for concavity. So sometimes this is just related to it. Sometimes I have a curve, and I want to know if my tangent line is an over or an under approximate. And look, if I'm concave up and I have a tangent line, then that tangent line is going to be a under approximate. But if I'm concave down and I have a tangent line, then that tangent line is going to be a over approximate. So don't get it confused with this, because sometimes we use it for that. This one, notice what it says, second derivative test, and look for local extrema. So what does that mean? Notice what it says. If the derivative is 0 and you're concave down, then it must be a max. Chav, why? Well, let's see. Let's do this situation first. So I have a derivative of 0 and I'm concave down. So here's concave down. And look, right smack at that point, do you agree that at that point that my derivative is 0? Well, notice, if I call this f, notice that this is a max. Do you guys see that? So if you have a critical value of 0 and you're concave down, it has to be a max at that value. That's all it says. Does that make sense to you guys? All right, look at the other one. Let's say this one says derivative is 0, and remember the second derivative is positive. That means that f is concave up. So here I am, concave up, and then look, notice, bam, right at that point, there's my 0. There's my f prime equals 0. So is that a minimum? Yeah, so that's all it's saying. So this is called the second derivative test for local extrema. If we just call it the second derivative test, that which one are you talking about? Like, it's just a means that you're just taking a second derivative to see what the concavity is. And because my derivative is 0, I either have a max or a min. Cool?
So here we're just trying to find max and min,
Yep.
while the other one we're trying to find concavity.
Yeah, on the other one, we're just bluntly just, what's a concavity? You know what I mean? Yeah, perfect conclusion. How do we feel, guys? All right, so look what it says here. Use the second derivative test to find the local extreme values of this. Okay, so my first move, take a derivative. F prime of x equals 3x squared minus 12. I'm going to equal this to 0 to find critical numbers. And these are candidates for max and min. So I'm going to go factor out of 3, and you get x squared minus 4. And I'm just going to, yep, I think we did this question exactly already. But the last time we did the sign chart or railroad tracks. So here we go. I'm going to take a second derivative. And I'm going to, what's the derivative of 3x squared? And I'm going to go f prime of 2. And I got 12. Now that's positive. So I'm going to say this. It's concave up at 2. And I know that at 2 I have a critical number. Do you guys see that? Because see how I equaled it to 0 and I got this? So I'm going to say this. Since f prime of 2 equals 0, and make sure you put the word and f prime of 2 is positive. So I'm concave up and have a critical number. What is that on f? It's a what? Is it a max or a min? It's a min. Draw a little figure. Look, see? 0, this is f. And concave up and a little point there, so it's a min. So yep, so I'm going to say, since f prime of 2 equals 0 and f prime of 2 is positive, comma, x equals 2, bless you squared, bless you cube, bless you fourth power, is a min on f of x. And I'm going to change colors to the blue one. Yes, ask me. No, for absolute, we have to test our endpoints. So these are everything that is, all max and mins are all local. Relative, but not all of them are absolute. There's only one absolute and one absolute max, one absolute min, if it's on a closed interval. And if it's not a closed interval, it's not guaranteed. What's up?
I thought you said that x is equal to plus or minus 2.
Yeah, I haven't done the negative 2 yet.
Oh, okay.
Yeah. See, that's why I changed colors. All right. F prime of negative 2 equals 6 times negative 2 is negative 12, and that is negative, so that means f is perfect. And because you're concave down, draw a little picture. Concave down, it's a max. You're on your A game today, miss. So I'm going to write since f prime of negative 2 equals 0 and f prime of negative 2 is negative, comma, x equals negative 2 is a max on f of x. How do we feel? Yeah, there it is. We probably could have done it yesterday, but we were just running out of gas.
What would it look like if we didn't have a max or
Like this.
like whenever we're trying to solve it?
See how the derivative is 0 there, but if you take the second derivative, you don't get a positive or a negative. That would have been like an example like x cubed. You just first derivative 0, second derivative 0, and so nothing. This is why sometimes we don't do this method.
So if we have like 4x and then we have to take the first and second derivative, there would be.
Oh yeah, linear lines don't have concavity. See? So the second derivative will be 0. All right, true or false? If the second derivative is 0, then c f of c is a point of inflection. Oh, that's tricky. Well, you might not know because you haven't been here. If the second derivative is 0, that's telling me I have a point of inflection no matter what. What do your instincts tell you? What does your intuition tell you? Yes? Oh man, your intuition's not. I'm not going to say sucks. Come on, man. You said that. All right, look, let's do an example because you guys are visual learners and you guys learn by counter examples. So look at this problem, x to the 4th. Do you agree that x to the 4th looks a lot like x squared? It looks like this. But check it out. If I take the derivative twice and I equal it to 0, I'm going to get a 0 at 0. Look, y prime equals 4x cubed. Y prime prime equals 12x squared. If I equal this to 0, at x equals 0, this is 0. But do I have a point of inflection? No. So I'm going to say false. And I'm going to put the answer. A point of inflection, a point of inflection occurs when there is a sign change in f prime prime. That's the same thing. Let me put this in parentheses. And I know, f prime prime. I should have called that f. That's a big deal. I'm going to put this in parentheses. Same as saying f prime changes from what to what? No. I put f prime.
Oh, up and down?
Increasing to decreasing and vice versa. Same as saying f prime changes from increasing to decreasing and vice versa. All right, so I'm going to stop. I'm going to slow down because I want to make sure that you guys really got it. If the second derivative changes from positive to negative, that's the same thing as saying f prime is changing from increasing to decreasing.
So is that whenever we plug in the x value they give us? Or the y
value? It depends because sometimes you remember yesterday, I have it right here. Remember yesterday we did it with a graph and we had an f prime graph and we literally said, look, f prime is decreasing. So that means f prime prime was negative, but we didn't say that. We just said, f is concave down. See? And yeah, we can infer that from that graph. Look, it looks like an elephant. So make sure that we got that down. And it does get tricky sometimes, guys. Let's see. If f prime is 0 and the second derivative is negative, then f has a local max. Well, let's see. Yeah, that's the definition. Yeah, that's a local max. Yes. This is definition of second derivative test for local extrema. What does extrema mean? Yeah, max or min. It's extreme. It's Latin word. Is anyone studying Latin? Oh, no? Okay. And at Burbank, there's a Latin course. Yeah, I bet. All right, here we go. The x-coordinates of the points of inflection on the graph, blah, 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 are. Let's assume we don't have a calculator. So let's see if we can do this. So I have to find the second derivative. So you can't get to the second derivative until you get the first. Y prime equals 5x to the 4th minus plus, okay, y prime prime equals
20x to the 3rd
minus
x squared
All right, equal that to 0 as for to find candidates for it, not that those are points of inflection. Factor out a 20x squared, and you're gonna get x minus 3. Are we still okay? Okay. X equals 0 and x equals 3. Be careful, do not answer the letter D, not yet. Railroad tracks or sign chart, call that y prime prime. 0, 3. Work smarter, not harder. Wait, did I say that right? Work harder? Yeah. Okay, because sometimes I mix stuff up, especially when I have no sleep. All right, that 20x squared, do I have to worry about it? No, it's always positive, so don't even look at that. If I'm to the left of 0, like -1, -2, it doesn't matter. -2 minus 3 is going to be negative. Yeah, all you care about is the sign, guys. A number between 0 and 3, like 1. 1 minus 3, negative. A number bigger than 3, like 5. 5 minus 3, positive. So this is my second derivative. I only have one location where the sign changes at 3. So where's my point of inflection? 3, and that's it. All right, that's it, guys. We're done. What do you guys think? Not bad, right? All right, guys. Just take care of the delta, and we'll call it a day, and then we'll practice some more tomorrow.